In this video, I'll talk about Geiger Method and the way to use Geiger Method. Geiger location algorithm is a basic yet powerful method to locate microseismic event. Each microseismic event has four unknown, the origin time t0 and source location x0, y0, and z0. Given the set of initial value for the origin time and source location, we can calculate the travel time residual at each geoform. In this equation, r sub I is the index for the geoform, and ti is the observed arrival time at the geoform I, t0 is the given initial value of the original time, and uppercase T is the travel time from the given source location to the geoform I. The travel time Ti can be approximated using Taylor expansion around the initial value. So delta T0 is unknown, and the delta H, which representing any of the variation in x, y, and z, is the other unknown. We can rearrange this, and we got the travel time residual R is related to the delta theta, and delta theta is a vector with delta T0, delta x, delta y, and delta z. Using a matrix formation, the vector of travel time residual equals a matrix A times a vector delta theta. The only unknown is we don't know the delta theta. So the Geiger location algorithm is to use a singular value decomposition to calculate the delta theta based on the travel time, the matrix, and the given initial value. The algorithm iteratively updates theta starting from the original value and until it converged. After converged, the location method finished. So this is the theory, and let's see how it works in InSite. I'm using a lab acoustic emission as example here, as you can see in this 3D visualizer. There are 18 sensors around the cylindrical rock sample, and the waveform looks like this. This is a synthetic acoustic emission, and therefore I know the location. The location has to be at 0, 0, 0 original point, marked by this dots here. To use the Geiger method, it's very simple. Go from processing settings at the left lower bottom and select the tab of locator, and then select the inversion algorithm, Geiger routine, velocity structure. We provide two velocity structures for now. One is a homogeneous isotropic and the other is time-dependent homogeneous isotropic. The reason is for the lab case, in particular, the velocity changes a lot and very quick. So you probably don't want to use a static velocity model for the whole experiment. You would like to use a time-dependent velocity model that you measured as you are performing the experiment. I'm going to use a homogeneous isotropic velocity model and then choose the phase. I'm only using P wave because, again, this is the lab case. I don't pick shear wave, but if it's a mining case or hydraulic fracturing case, you're definitely going to use both P and shear wave. The minimum P wave arrival is 4, so if it's less than 4 peaks, the location will fail. I'm not using shear wave, so the number here is 0. That's pretty much the settings you need. You don't need the parallel processing because this algorithm is already really fast. So once I'm done with the setting, I click OK, and I come back to the waveform and I click locate. And the result is instantaneous. And in my computer, which is 4 years old, it takes 4 microseconds to finish the processing. So it's very ideal algorithms for people to process if there's tens of thousands microseismic events to locate. I can check the quality by going into the 3D visualizer, and we can see the events located right where it's supposed to be. So it's pretty accurate when you have a 3D coverage of the volume there you're looking at. Thanks for watching. In our next video, we'll talk about simplex method.